Okay, so our agenda for today is to compare two different kinds of equilibrium constants. Now, they're both equilibrium constants, but they have little subscripts here telling us what kind of specific situation we're dealing with. Now, they're both KEQs, so they're both dealing with the ratio of products over reactants, but the kind of information that's going into this equilibrium constant is different, and that's why we're giving them different letters. But don't get lost in the fact that they're both still equilibrium constants. They're the ratios. All right. So I wanted to compare KCs versus KPs. When you see a KEQ written as KC, what that's telling you is that these are based on concentrations, specifically molarity. And that's where the C is coming from. All right. Now, when you write a KC, all right, you're going to do, the products raised to some coefficient, all right, based on the coefficient from the balanced equation over the reactants raised to its own coefficient. All right. But I'm writing square brackets here because the square brackets tell us what?
Concentration.
Not just concentration. What kind of concentration unit? All right. Well, square brackets imply what concentration unit? Molarity. All right. So if you're based on molarity, you're going to use square brackets, and you can call it Kc if you don't want to call it just plain old KEQ. All right. What do you think a P means in Kp, George? Pressure, right? So if you're working with gas pressures, you can write your KEQ expression and do the calculations based on the pressures of the gas involved. All right? What pressure is, the partial pressure due to each gas. All right? Now, when we write a Kp, we can't use square brackets. All right? So you might write the pressure of gas, D, raised to whatever power. All right? But you don't use square brackets, guys. It's a convention, but you do want to pay attention to that. So you would write parentheses around P, whatever gas it is, raised to its power, and so on. But mathematically, these guys work in the same way, all right? Products over reactants, you raise it to the coefficient, and so on. So in some ways, these are very similar, but it turns out that for a particular system, the value you get for a Kc and the value you get for the Kp may not match. It depends on the reaction. All right? And so one thing we need to be able to do is to go from a Kc to the value it would be for the Kp and vice versa. So I want to show you how to do that. There's a really handy equation, and it's on your formula sheet. So if you look on your formula sheet, there's an equation that relates Kp to Kc. Can you guys all find it on your formula sheet? All right. So it's there. It's on that green sheet. So it says Kp is equal to the Kc times RT raised to delta N. And I believe it even tells you on the formula sheet that delta N is moles of gaseous products minus the moles of gaseous reactants. So it's not total products minus total reactants. It's gaseous products minus gaseous reactants. All right.
Oh.
Yeah.
Can you use Kp when you're dealing with changes that have both solids, liquids, and gases, all three?
Yes, because only the gases would affect the KEQ. So if you're working with gas pressures, you can call it Kp. All right. And if you've turned it into molarities, you're really working with a Kc. Depending on the equation, though, if you have different numbers of moles of gas on the reactant side versus how many moles of gas you have on the product side, you're going to get different numbers if you're working with pressures versus concentrations. All right. And so that's what we need to look at here. All right. So let's go on and look at some equations where we can calculate delta N. If you can calculate delta N, then it's very easy, really, to convert from Kp to Kc and vice versa. All right. So let's look at this equation. We've worked with this equation before. We've done some problems with it. We have 2NO reacting with chlorine gas to form NOCl. All right. How many moles of gas do I have on the reactant side?
3.
All right. So there are 3 moles of gas on the reactant side. How many moles of gas do I have on the product side?
2.
All right. And we were just looking at this. So we can calculate delta N. All right. We said that delta N is moles of gaseous product minus moles of gaseous reactant. All right. Well, we just figured out how many moles we have. So we have 2 minus 3, or N is equal to -1, right? So if we look at our equation, where Kp equals Kc times RT raised to delta N, that means Kp equals Kc times RT to the -1, right? Which basically is Kc over RT, right? You want to be able to do these conversions. I need an equal sign there. All right. Is it that hard to do? No, but you have to remember to do it, and students forget it. Don't be that student. Be the student who remembers to look at moles of product versus moles of reactant. And you've got your formula sheet, so that does help, at least for the free response parts. Should we look at another example? All right, let's look at this. Now, what do we know about solids in KEQ expressions? They're not included. All right. How many moles of gas do I have on the reactant side? 1. How many moles of gas do I have on the product side?
2.
All right. What is delta N equal to? 1. All right, because I have 2 moles of product minus 1 mole of reactant. I'm only concerned about the gases. All right. So we know that since Kp equals Kc times RT raised to the delta N, all right, we know that Kp equals Kc times RT. All right. Is that very hard? No. All right. You want to be able to do these conversions, and then if you have a numerical value for Kc, you can plug it in. R is the universal gas constant. T is whatever temperature you're at. T is the only thing that really affects KEQs. And you could calculate Kp or vice versa. So you should be able to do that, but you have to know how to work with the equations. You guys all feel comfortable with that?
Yeah.
Excellent.